Cracow and Oprocha, very close, but on backside. The title is on pseudoarc and dynamics, and this is a talk written seminar on dynamical systems with Ivan and Simon Semester. See you soon.
Thank you very much. Always a pleasure.
Press what it's.
That one. Okay. I understand. Okay, thank you.
I will not repeat everything.
It's always good. Thank you for coming after lunch. Right, so in this talk, I will try to give you information that I gathered over the years, what I learned about pseudoarc, and background story will be two projects that I was involved. And that's all that I learned very much, and I will try to do it during this talk. So I will try to give you at least flavor of some techniques that we were using and how they may be applied to possibly different topics. And most of that will be based on these two papers. So first part will be related to work with Jan and Tierney, and the second part will be kind of follow-up or related topic also about pseudoarc, and some tools will be also coming from that cooperation with Serge and Joseph. So at some point, Lebesgue measure preserving maps will be important, and we'll enter this topic, which seems quite different at start. All right. So the main object for that talk will be pseudoarc, which was discovered, as you see, more than 100 years ago. So it was a time of development of topology, and people were excited about new interesting objects. And Knaster found out connected, so continuum for me will be compact connected set. So he developed example of some continuum in plane, which was hereditary in the composable. So the composability is normal thing that you have from standard spaces like arc. So if I have arc, I can always take two subarcs, this one, that one, and they will split the space. I can present always arc or any subarc. I can present as union of two subcontinua.
Let me ask, Knaster was in the Bonn for long.
Yes, I think so.
And then he moved it to Wrocław and founders of topology.
Yes. Yeah, lots of development in Wrocław also. Right, so the composability means this exactly, that I can find two subsets connected which is in the space. And then in the composability means that you cannot do it. And hereditary in the composable means that even if you like restrict to subcontinuum, you still cannot decompose it. So in some sense, it's very, very different if you compare to arc, right? Because in arc, I can decompose, I take subcontinuum, which is arc again, I can decompose and so on. So yeah, when I don't know if you have seen this definition before, but when I saw it the first time, I said, okay, that's impossible. You cannot have something like that because, well, no, take two continua, they intersect, and then you have something you can decompose. About little hooks. So here, what happens is that, first of all, there is no arcs inside, of course. And second, you cannot find two continua like this. So if you take two of them and they intersect, one has to be subset of the other, because otherwise you can take union and you have something you can decompose. So it is something really, really strange if you start to think about it. I will tell you a little bit more how you can get it. It's Pierne last week said a little bit about it. So no picture, as you can expect after his talk. Okay, and there is this arc-like. So I said this was in the plane, but usually you say, if you define pseudo-arc, you say arc-like hereditary in the composable. So arc-like means that if you have your object, you can find, well, abstractly, but you can find arc, which approximate it in the sense that if you project onto this arc, then for every epsilon, you can find arc such that you can project on it, and fibers are of diameter at most epsilon. So this is what arc-like means. I can take my very strange object without arcs, and somehow for every epsilon, I can embed it into arc in such a way that fibers are of diameter epsilon. So in some sense, it's similar to arc, although it's not arc. Okay, so that's what Knaster found out. And I suppose he was very excited about this. And then several years later, people start to find out again strange objects of similar flavor. So the second example in the literature I want to speak about is by Moïse. So he found, again, it was in plane, some continuum such that that one, it was in some sense similar to arc. So it had the property that if I take any subcontinuum, it's like smaller, let's say smaller copy of the whole thing. So homeomorphic copy of the whole thing, right? So he constructed something like that. And it's why he called it pseudo-arc, because it was not arc, but had this nice property like arc that every subcontinuum is a copy of everything. So you may think, okay, this was something like maybe fractal structure. It's in the plane, and then you plug out something smaller, but it looks exactly up to homeomorphism as the whole space. So that was second. And third one was by Bing. And that one was similar to circle. So this is this definition of homogeneity. So you have definition here. I hope you can see it. So the property is that I have this continuum. I fix any 2 points, and I find homeomorphic sending one to the other. Okay, so it's like on circle. On circle, you will have rotation. Here you can somehow construct this homeomorphism, and it's not circle. Okay, so his example. So that one was maybe similar to arc. That was similar to circle. But was not circle. Okay, so this was discovery on strange geometric objects in plane.
Were these all hereditary?
That's a good question. So it is what they had, right? 3 examples, quite different ones. Yes, and the answer is here.
The last one by Bing, why is it not a circle?
Because he proved it's not circle. Right? Yeah, so it is why he found something which was similar to circle but was not circle. Okay. Right, and then it's what Bing proved 3 years later. So he proved that all that examples are in fact one example. So they are homeomorphic. And that's also a surprising thing. Because if you look here, that if you just see this definition, they do not look like the same thing. And motivations were different, but at the end, they were the same. So that's maybe the most common definition of pseudo-arc that people use nowadays. Arc-like hereditary in the composable. But it has also these properties that you see here. Yeah, so also I didn't say that, but it's not plane separating. So that's one of the arguments maybe why it's not circle. All right. So that was quite surprising. And that for me is even more surprising because it says that if you use topological lengths, so if you use Baire category theorem on plane, for example, then that what we will get as typical continuum is that very, very strange continuum. right? So if you think about like typical example of continuum, you probably won't think about this hereditary indecomposable. For you, probably that will be the most common one.
If you allow everywhere small bushes to grow up, then it's possible.
Then, but you cannot remove them.
So that's why it is difficult. Am I right?
Maybe. Yeah, you can always like somehow destroy this nice structure.
But not vice versa.
So of course, with typical is like, you know, rational and irrational. So irrational are typical, but rational you expect or see more often in some sense. So it depends how you look. Okay, and that's I'm just showing it's not completely related, but it shows that with this pseudoarc, in some sense, they were lucky them, but it was being so there are not many continua that you can have with this homogeneity property, right? Because circle was obvious, that one was example, and then there is one more and nothing else up to homeomorphism. All right, so now let us turn to dynamics. So of course we are interested to study maps and some iterations. And then if you want to like design some dynamical system on this really strange space or on some continuum, then you need some tools. And here you have two probably most common. So the first one, that on the left, it's how you can try. So if you know how your space looks like, so here you have Knaster, bucket handle continuum. So if you know how it looks like, you may try to do the following. So you start with very, very rough approximation, and you put some map there. And then you take better approximation, and you probably, if you start on that big one, probably it won't preserve that smaller thing. So you will have to like change it a little bit to make this invariant. And then in next step, again, some part will go out. So maybe this more fine approximation won't be invariant. So we will have to again change your map and so on and so on. And then if you do it properly, then maybe you will get Cauchy sequence of maps, and at the end you will get something that lives on the intersection of all that objects approximating. So your continuum will be intersection of that sequence. And if you do it properly, at the end also that what remains on that that intersection will be well-defined map. Of course, you have to be very careful because it's easy to destroy continuity. So we
Cauchy in out of this one.
Cauchy in space of maps. So I take maps, like maybe on disk with suprametric, and I construct these maps and hope that it will break.
These maximums go completely. I don't think it's Cauchy sequence.
Yeah, you have to do it like that, right? To have your map at the end.
Here from the picture, it follows Cauchy sequence.
No, so here is set, right? This is
Yeah, so I mean, not mention what Cauchy sequence.
the way I have like KS. I'm intersecting them, and on the intersection, I want to have Cauchy sequence of maps. So that,
Okay.
well, maybe not on the intersection, but on.
Oh, no.
The picture shows Cauchy sequence and out of distance.
Let me maybe we understand
No,
each
but
other.
it's not important.
So what I would try to do, I would like construct some sequence. One of possibilities, of course. Here is like bigger set, and I would like to have this. Maybe even equal. Okay, and then I hope that these maps converge to something, and then I will get something invariant on this intersection. That's one possibility. I could do that. Maybe I can also forget about exterior, and then I have more freedom, but have to be maybe more careful just to show that this map is well defined. All right, so that's one possibility. So for that, the hard part is that you should more or less know the shape and be very careful about this convergence. And of course, at the end, probably you want to have some extra properties or at least be able to say something about that map that you will construct at the end. And that's hard part of this approach. That one is in some sense easier, the second one. Easier in the sense that you can use the development of topology over the years. So what's the approach? So here, as you see, I have some space, call it X, and I have map on that space. And then I take countable product of X and I consider sequences there, but with this property of map F involved. So I construct inverse sequence. I just previous position tells me which is next one. So I like extend backwards. And this is well known that if I start with compact set and continuous map, then that space of inverse sequences in the product, in the topology induced by product from product will be compact. If I start with connected set, it's connected. So, like for example, if I start with interval, I will have some continuum. The hard part, which can be easy, is in that F. So nice situation is that if I know what maps to use to say that X is my continuum, right? That would be, so instead of display, I would maybe somehow take out from somewhere in the literature what F should I take so that this X is homeomorphic to my space. So for Knaster, for example, tent map is good. For pseudoarc, there is something different. I will also tell you a little bit about it. How to find map that you will get, that you will give you pseudoarc. And there is literature about it. So what you can use. Okay, what you get.
Send this sigma F is X0, then it's 0, X1.
Yeah, so I apply F to every coordinate. But in fact, that image of that one is this one. So we just shift to the right and calculate.
This S and backward.
Yes.
Okay.
Yeah, but in fact, it's application of F on each coordinate. Okay, and of course, that's clear that I have inverse of that map. I just hit out the first position. So this gives me homeomorphism. All right. So
that's one.
Yeah, so people call it natural extension usually. And it's, so I get homeomorphism just for free using, of course, that map is not invertible, but this one is. So if I know that it is, for example, pseudoarc, I for free get homeomorphism of pseudoarc. There are many properties that are shared, like entropy is the same, periodic points, it is easy to see that they will generate and so on. So many dynamical properties will be like, go for free. The problem is that maybe, and that you will see later, that not every dynamics you can construct that way. That's difficulty. Right. But still, it is very nice tool and very effective one. Like if you look for examples on some strange continua, that may be a good idea is to look for put F, and then you will have your homeomorphism instead of doing this. But possibly this gives you more freedom and more options. Okay, and here are two results that I want to mention. So we are working on some really complicated space because pseudoarc seems quite complicated. And then what happens sometimes that the space is so rigid that it forbids some dynamics. And here you have one of examples. So this is by Henk, Bruin, and Sonia. So it is for inverse limit of 10th maps, but like shorter ones. So I take 10th map, I produce inverse limit. Here you get some space, which looks like Knaster continuum, but with some terms in some maybe random places. And what happens is that allowed values of entropy depends on the space, right? Because I take this space and here I cannot get any real number. I have some gaps. And it seems that because of the shape of the space. So space is complicated and it has some impact on the dynamics, possible dynamics that you can see. But it can be even worse. So this is kind of classical example, so-called Cook continuum. So there is nothing interesting going on that space. So it's so rigid that it's really kick out most of maps. So you can have constant maps or identity, nothing else. So what I'm saying is that structure of space can really influence the dynamics you can see there.
Do you mean the theorem by Brown and Tillman that the only homomorphism is just F and it iterates? There are more.
I think there are more, but this is about like.
No, I'm just guessing.
You can slide along.
I see.
But they're all
Some lines where you can have some prisms.
they're all on the same isotope.
Yeah.
As the iterates.
Okay, so now a little bit how you can construct pseudoarc using inverse limits.
Groups, of course.
Yeah, across the median, yeah. If. So it's like dishonest, ultra dishonest. Okay, means dishonest.
Okay. Right, so what's the property we are looking for? So we fix some delta, and then we expect from the. So what's the property I want to have? So if I have two values. This and up is going here. So I take 2 points that give me that value, and then I have to be able to like interwind them. So here I should give those to B at distance delta. The same here. So the graph should be like. And this must happen as long as these values are more than delta apart. Okay, so because that's the mechanics piece of before that condition, right? So I have values, and then I can interwind such that I'm delta close in opposite order. So of course, because of that, probably here there will be interchange and here interchange and so on. So the graph will look more or less like this one. So that's example how you can construct it. And there are like algorithms how you should do it. You have to go a little bit up and a little bit down, then maybe more up and then come back and so on. You have to introduce lots of zigzags in the graph before you can move from one corner to the other. And what is also clear that I cannot have this condition for every delta because then I will break continuum. So if I can have this condition, then it's for some delta, and after that it won't work for one given map. Because I will simply destroy continuity. Okay, so that's it, but still, for every delta, there is method how to even perturb identity to have this property. All right. And the main reason for this property is this theorem by Means and Transue. So they say, okay, if I find map on the interval such that for each delta, maybe not map itself, but some iterate will have this crookedness property, then in the inverse limit, I will have pseudoarc. So that was theorem, but there also was a technique how to get it, and it was by perturbation. So they were starting with piecewise linear map, and then so they were starting the F, which was mixing, and then here they were composing it with some maps, and it was converging to the map. I think maybe better. And it was converging to something at the end with the property that they want. So this is perturbation technique, and it's obtained more or less by composing with maps like this one. So they take smaller and smaller perturbations of identity with smaller and smaller delta in the definition and composing it. And the process depends on map you start, and then successive constructions of next map. That's what's in this paper. It was from '91 and published in Proceedings. And the reason for that was, I will speak a little in a moment. Okay, and I believe this.
X for the natural extension. What is X?
Yeah, this is inverse limit with F as bounding, as unique bounding map. Right, so if you look into that paper, you see how you should do that. Okay, so that's also a good paper to learn how to perturb maps to get pseudoarc. And that technique gives lots of freedom. You can adjust it to your own needs. We're doing this several times. Okay, and here is a picture from Means and Lewis. So this is graph of map. So they write here sigma 200. I believe that delta is for crookedness is 1/200 or something like that. And this is what you get if you try to draw it. So either not rough because it's disconnected, or quite like region. And that happens if you want to draw pseudoarc as well. So if you try to draw pseudoarc, and they prove it in that paper, is that either you will get something which is not connected, or you will see some chunks which will make it looking not one-dimensional. Okay, so this is one-dimensional space, but if you try to draw it, it looks like either not continuum or
like Sierpiński curve, where you can do this. There's a square shape was.
yeah, similar. Yeah, you definitely have lots of zigzags.
Yeah, this Sierpiński curve.
At least it looks.
Yeah, no, I say in general, what you are talking about.
Yeah, it's nowhere differentiable, that's for sure.
Contraction of these
Yeah, so
this continuum construction of Sierpiński curve. Like this. Of course, there in the limit is the whole square, so the result is not what you would expect.
yeah, so here probably you might make it like some region, but still, if you try to draw it, it won't be like dimensional. Right, and that is approximation of that map that you use here, and here is probably the first, at least the first I know, example of pseudoarc as inverse limit with one bounding map. So this is X squared with some notches or some small perturbations. And then Henderson proved that how to make these changes, and that is pseudoarc at the end. So from dynamical point of view for that map, as you can see, there are only, because diagonal is here, so there are only 2 reference points. So this is example of map with 0 entropy. That's the more important later on. Okay, so the first example giving pseudo-arc was giving homeomorphism with 0 entropy. Those ones will give positive implicit. Okay, so one of the questions that people were working first was about transitivity. So they were asking what about transitive maps of pseudo-arc? And this question was solved in '91. So there were papers by Judy Kennedy, and she was using this first approach that I showed you, that she was like drawing pictures in plane, trying to approximate pseudo-arc, because there is also a method how to see it. And what she proved, so that example that she obtained, it was transitive homeomorphism, but it has property that it was extension of 10th map on the interval. Okay, that is also important, that her example was semi-conjugated to interval map. And she had also some other understanding what can happen in pseudo-arc. This is also quite interesting, that you can take contour set and dynamics on it and you can extend it. And at the same time, exactly '91, this paper by Mitz and Transue appeared, and it was using, as I told you, inverse limits, and it also leads to transitive map. Okay, so at the same time, 2 different techniques resulted in transitive map on pseudo-arc. And the question was, if I remember well, from '89. So, and most likely asked by Marcy Barch. So he asked about transitivity, and then solution came out by completely 2 different techniques. All right. By the way, this is Judy Kennedy, and Yarnay, you saw him here. And I like this picture because it was taken just before COVID came. So yes, a little younger. Right, and it is what I said, that papers of Judy, they give some different insight into dynamics in pseudo-arc than inverse limits. Okay, so the first question, or the first result will be here, is about entropy of maps on pseudo-arc. So also from '89, there was question what values of entropy you can get in pseudo-arc. And of course, the first setting you may try to answer is shift homeomorphism, so this inverse limit with 1 bounding map. And that's one of the first results. So what Bloch, Kissling, and Uspensky proved is that if you have pseudo-arc given by 1 bounding map and you get it as inverse limit, and entropy is positive, then you will find 2 Horseshoe for second interval. That's exactly what they do. Okay, so that gives you this bound.
In the last result, you showed the semi-conjugacy is on the inverse limit space.
So
How compared to the benchmark?
So in that result, I have this pseudo-arc, and I have here some homeomorphism. So it was just constructed, so it's not too inverse limited. Then I can find continuous map into interval and 10th map. This is the full 10th map. And this is semi-conjugacy, right? So it intervenes the dynamics.
It's a factor of the
Yes. It's extension of the map. Yeah, our 10th map is factor of that guy, transitive guy. Right. Okay, so this was the first one, and then Chris Moron, he was working on it quite intensively, trying to say what entropy you can see, and then he proved 2012, he proved a little more general theorem that I'm showing here, but for this talk, it's enough to show that one. So consequence of what he proved was that if I take inverse limit and the shift map, or if I'm able to factor onto interval map, then that's the only values of entropy that I can see. Okay, so if I'm here in Judith Kennedy transitive map was extension of interval map, or if I use shift homeomorphism, I cannot see any different numbers. So in fact, that is very overshooting, let's say, right? This is in fact infinity. And then if you look into that proof, and the reason is that because of that crookedness, horseshoes start to grow very, very fast. So you move to higher iterates, and then you have explosion of horseshoes. They like start to, not like standard way, but they start to, like new elements of horseshoe appear. And it's why it pumps up entropy to infinity. That's more or less intuition. Right, and so in fact, after that theorem, you find yourself into the situation that all examples, or at least it was for us, all examples we knew were only these two values. So Henderson, I showed you, zero entropy, nice example, and means transu, whatever you construct, it's transitive map, so it has positive entropy, so immediately it has infinite entropy. And nothing else, okay? So after that, you may start to think, okay, maybe that's the case. Right, and I said that what Chris proved is it was a little bit more general. I'm not showing this definition, but it was related to some kind of stretching. So he said, okay, if you observe that map somehow behaves on covers of the continuum, then entropy have to grow. More or less, that's the. Okay, and here is example that I discovered or I learned with Jan quite late. And I'm showing it because it's very surprising and quite beautiful and maybe a little bit forgotten. So you see like 80s. So this was constructed by Wayne Lewis, published in some Mexican journal.
Looks like it was higher.
Yeah, so okay, so what's on that picture? So this is sketch of bounding map. I will say a little bit about this example because it's a really beautiful one. And it's like red compared to what before. Okay, so the example use triod, but in fact you can use it. So I have triod. Right? But it works for any. Triod is maybe the first worthy to look. And then I take that left and I start to put it on triod. And that's how more or less it looks like. So it looks like a little bit to the right, more down, more left, and so on and so on. And it's symmetric. It's done symmetrically. So you make like it's on the circle and you have this symmetric way of like, I think like more here, and there are formulas how much. So he just divides each leg into some number of pieces, and then each piece is stretched. Not like a leg. There are some proportions of the lengths, and there are some formulas how you should do that. All right. And this map is, and this triad, but also map, it's commuting with rotation. Okay, so he do it, not sure if it's visible from here, but what he is doing it such a way that it's commuting with rotation. So I have this map between triods and it commutes with rotation. And then what he do, he take sequence of maps. So deeper in the sequence, more these crooks, let's say, more this, more of that intervals and more walks around. So this increase, but in each step it's commutes with rotation, and then he takes inverse limit. So at the end, he has something which is commuting with rotation on each coordinate. So what he gets at the end is one fixed point and all other points of period phi, that particular example. But what is surprising here that he starts with Piotr, which definitely is not arc-like. You cannot project it into arc with small fibers. But what he gets at the end is arc-like, and it's fact it's pseudo-arc.
When you say inverse limit, because I understand we should think about the pseudo-arc as living in the plane, right?
Yes.
So this is not like the example where you took just some intersections like with the banner. So how, so like, let's say that you would go several stages, then how, so they get closer. It's like an inverse limit in house government?
Yeah, so I take like product. So in that case, maybe infinite product of triads, and I consider sequences. So of course you don't see what it is if you like look at these sequences, right? Or even in that case, I started at first. Maybe that's important to understand. So I had inverse limit of arc. So there was one map. There was infinite sequence with the property that previous one gives me the next one.
No, this I understand, but let's say this is the abstract representation, but how should we imagine it in the plane?
You mean here?
No, the slide.
Yeah, so I just, okay, so imagine this is this, I draw it, and then I define how images of these guides go around, and it's commuting with rotation, okay? Of course, I can do it in abstract way, saying, okay, forget it's in the plane, but the plane will be important in a moment. But at start, you can make it abstract. I simply have map, which gets one fixed point and somehow goes around, and then I have formulas how to put that guy.
You're taking the limit of the maps or the space.
I taking. So I have in that context, I will have this triad. I will have some map, P1, that first one, by 2, and so on. So this will be sequenced using different maps. And this also gives me continuum. But I have property that here there is rotation that there is.
So you're taking the inverse limit of the sequence
Yes.
of the infinite composition.
Yeah, so I take inverse limit, but here I have like second copy to write it. Okay. Here I have this rotation on each coordinate. And it's commuting. So it gives me homeomorphism on that space.
So it's in the plane because of ground state. So
Yeah, at the end it will be yes. But of course, at the moment I do it like abstract. Right. Okay, so yeah, so what I'm saying, the surprise is that I had this riot, which is not arc-like, but at the end I get something which is arc-like. And maybe one word of comment how it is done. That's quite interesting. So much of this is good calculation, but what he do is that he has the sectors. Then, depending how the rotation goes, so here I mark one sector, here 2 and here 3, and all of that goes to 1 point, and then the rest they go into intervals. Second one, so on. So he just collapse here something which is not symmetric, and then his next intervals for that construction he just projects into interval. So why he do it that way? Because now if you fix some point here, so we will go to these 3 places. But then because of this procedure that I go around, I apply this bounding map, then all of them will go to one leg. And then he makes it so careful that they will stay close in some sense. So that's the idea, what is going on here. So he make use of this bounding map that they are very special and they go around. So then, because of that, he calculates that in the future, these points have to be close. And all of that is about very careful calculation of these expanding factors, of type of these intervals, and so on. But still, that's tricky part of that. And of course, he do it like this, that the deeper he go, the smaller are fibers. So that's okay. But what about this example for our case? So, okay, so first of all, the map you have here, one fixed point, all other points of period 3. It is also what he said, and I will even use more of that later on. So what you can do, you can just make it fly out on the disk. And because of that picture, you see the image of this triad is some curve. So what you can do, you can take your triad, make it image in the disk like this. So this is homeomorphic on the triad. Here put identity, extend to the homeomorphism of the disk. And then you can make like homotopy, like starting to collapse it so that at the end, the image of triad is in triad. This is so-called almost homeomorphism. And then there is theorem of Brown that Phil just mentioned. I will also speak about it, which tells you that in fact, that thing lives in this, okay? Because if I have, if I take inverse limit using maps that are uniform limits of homeomorphism and the same space, then what I get at the end is the space. So in that case, this. It will be again on some slides later on. So what I'm saying is that construction, it lives in the disk. And it's one fixed point and all points of period 3. And it's, well, very hard to imagine how it's possible, right? Because space somehow looks like arc, but then you have these periods. So definitely on arc, it's impossible. I mean, to see movement like that. And okay, and this technique, you don't have to use triad, you can use anode, and that's still okay. And if you look into the paper, then you see on that picture there is no crookedness, because what Louis says, yeah, so that is this construction, and then to get pseudoarc, make it more crooked, and it will work.
There is this branching point, which works. Okay.
But at the end, there is no branching, in a sense, right? I mean, he's on each level, but at the end, it's hard to say how this.
Understand that if you take arc, understand what is the inverse limit, and an arbitrary vector trajectory until you capture like everywhere, two things.
Yeah, in a sense.
Hola.
In a sense.
Understand, we have such experience that to understand inverse limit, you would choose an arbitrary vector trajectory and full vector component. And then either you want one, then you obtain standard cluster, or if it's time to time not one-to-one. And then branching. When there is topology for inverse limit, you need to go arbitrarily far to the right. See what is topology there.
Yeah, so definitely you have to destroy arc somehow, right? And this is what you need.
Somehow you destroy the you obtain.
right? And then what you can do more, so you can, instead of that, just this rotation, you can take that guy and then make inverse limit again, but like increasing periods. So this is becoming more abstract now. And what you get at the end, you will get pseudo-arc with, instead of periodic points, you will have odometers. But the problem is that now it won't live in the disk because you have, I'm taking n cover of the space, and then I have this one bad point which I can get rid of. So like inspired by Lewis, and in fact he mentioned that you can also do that somehow. You can get example of map on pseudo-arc such that it has one fixed point and all others are odometers. So lots of odometers living there.
What does it mean for us? I mean, the closure of odometers and then has many orbits.
Yeah, so I have lots of odometers there.
Each other is in a orbit.
Yes. Yeah. So there is this fixed point and huge collection of odometers.
There's uncountable collection.
Yeah, I think so. Yeah.
Invariant.
Yeah, definitely uncountable. Yeah, so that's what we get there. Okay, and why we need it. Okay, so this is the theorem that I want to show you as first one. All right, so I was quite long working with Jan on this question of Marcy-Barch. So this was published in Contemporary Mathematics in '91, after this conference in '89. So when Louis just collected questions and then they published them. And it was about values of entropy. So what we were able to prove is that any value you want, you can get in pseudo-arc. All right, and maybe a few words how we prove it. Okay, one comment is also that sometimes you need luck in your research. So we were trying many different approaches to solve this problem. Usually it was like I discuss with Jan, then drive back home, and then we make call saying that there is counter example to our proof. But then somehow by accident we learn about that paper. So Piotr and Lou was visiting Cracow and we were working on some different things. And then at the end he said, oh, I was in very nice workshop in France about manifolds. And there was this paper by Beguin, Crevissier-Laroux, and this is method of extension of maps. And he told us what's in the paper. So paper is like maybe 60 pages long or like that. And there is lots of axioms like A1, N2, A3, B1, B2, B3. So lots of axioms. So it's very systematic, in fact, very useful if you understand what's there. But I think if we didn't meet him, it would be beyond our motivation. But he was there, he told us what's the main result, how it works, and then it became very useful. So I will also, I should talk about techniques, so I will also speak a little bit about that. So this is unrelated result, but quite beautiful, I think. Probably some of you heard about it, because it's kind of classic. And these three guys, they made this technique more accessible, more readable, and also extended. Okay, so there is technique of Mary-Rees. So this is about torus. So maybe just to make it slow introduction. So like if we are on circle, then probably most of you heard about Donjoua extension. So simply the method is that I have rotation on the circle and I blow up points and they start with stick intervals in the projectiles. So this is like standard Donjoua extension. Then densely I will blow points and put intervals. It won't be transitive then because I will have this wandering interval. Right, so that's what you can do on the circle. So definitely, if you do it that way, you will lose transitivity. But on torus, you can do similar thing. On torus, I can again blow point, but now I can start inserting intervals. So I have rotation, irrational rotation on torus. I do it. So the first observation is that I won't, if I do it carefully enough, I won't destroy minimality. So I will put some wandering interval, but it won't destroy minimality. But of course, from point of view of entropy, for example, it doesn't change anything. And then the question was, okay, so can I on torus find some map with positive entropy and minimal? And that's what Mary Rees developed. So she built techniques such that again, you can blow up, but this time not one orbit, but huge set, put inside some dynamics, but not destroy, don't destroy minimality. Okay, so this is, with that one, probably you can develop your own technique. With that of Mary Rees, that's much, much harder. And then what is in that paper is, first of all, like axiomatic way, what condition you should check to perform this type of construction. And second, what you get. So what they prove actually is that if I'm in that, if I'm on that torus, if I have some invariant measure, then I can now take contour set. I can take any measure I want there, and I can make such replacement here by some surgery and some systematic changes, such that at the end, this mu will change into product measure and all other will stay the same. So they just show that isomorphism of that space and show that how to do it such that I change my measure into some other. So now, if you have it at hand, you can imagine how you get this positive entropy. You simply start with rotation, you have her measure, and you change it to measure, and here you take something with positive entropy.
Not destroy minimality.
Yeah, so the technique is what you should do to not destroy minimality. So that is special modification of contour set. So here you select some special contour set and then very slowly change the dynamics. Very, very, very. So this is very involved technique, and this is why there are so many axioms and things that you have to take care of just to not break minimality. And what they also say, in fact, you don't have to start with minimality. You just, what you in fact need is non-atomic measure. Okay, so for this technique to work, you need non-atomic measure, and it is why we use that Lewis technique. It is why we needed odometer, right? Just because that was the first prerequisite to that. Okay, this works for manifolds. We didn't have manifold, unfortunately. But okay, somehow because of understanding of the space, we were able to have the same conclusions. And what is also some comment. Okay, so what I'm doing, I simply so I have that original map on torus maybe, and I extend it. So here some number of trajectories that are changed to something. All right, so if the map was minimal, then you can imagine I can do similar thing as I told you about this kind of Donjoua extension. It is two-dimensional, I can put one-dimensional things, and maybe I won't destroy transitivity. But the problem is that if I try to do it, and instead of the minimal map, I start with some invariant set. So if I have here some invariant set, and I like repeat this technique, it will work, of course, for the whole map. But the problem is that because of the process, I don't control exactly what this guy will change to, because there is lots of deformation going on. I had some contour set, I changed it to something completely different. So if it was not the whole space, but maybe something one-dimensional, then it will change to something else. And for example, you can imagine that I start here with Knaster continuum. With some measure, I make this technique, right? So it was maybe Knaster continuum, here was some measure. I apply directly this technique, I get that extra measure, but the problem is that that guy here is no more Knaster. And because of this result of Stimmage and Bruin, in fact, it cannot be. If I take here map with any entropy, then I know that some of them cannot exist on Knaster continuum. So this may deform very much the space, and there is no clear way that your continuum will survive. Fortunately, with pseudoarc it works. Okay, so and the reason, some of the reasons with it seems to us it works because of this grouped shape, that if I deform it and I do it in proper way, this deformation won't deform the space more than it was deformed before, something like that, because it's so fractal-like. All right. So that's about flavor, and as I said, if you are interested, this paper is really nice, and I believe it has lots of applications, possibly with different contexts. And in some sense, you don't have to work that much if you fit exactly into the setting.
What do you think about break?
Good moment.
10 minutes.
Yes. Maps. I won't tell you that much about them, unfortunately, but I want to show you one technique which I think is more beneficial. Okay, so anyway, so now in the setting, there won't be just interval maps, there will be maps preserving Lebesgue measure. And just to remember is that if we use metric of uniform convergence, it is still nice space. So it's complete space, and we can speak about generic properties and use Bell category theorem for that maps too. And all right, so that I will keep. We will come back to that. The one comment is that if you want to work with this Lebesgue measure preserving maps, then you cannot make arbitrary changes, because if I add in graph some random change, probably I will destroy Lebesgue measure preserving. But what I can do that what you see on that picture, I can like repeat parts of the graph. So Bobok and Trubetskoy call this folding. Right? I take these values and I like squeeze it and repeat 3 times. It will still preserve Lebesgue measure. Right, so that map comes from this one by repeating. So that's one of the techniques that you can work when you deal with this map. That is allowed, but I cannot like move this a little bit up, because then I will destroy Lebesgue measure preserve. So you can make many things, but you have to be careful. But that I will speak. So we were interested in pseudoarc. So that picture I showed you before. So definitely these maps are not Lebesgue measure preserving. And when working with Yerney, we really wanted Lebesgue measure preserving, so we had to change something in this graph. And this is what we did. So somehow we combined that method of means and ratio. So here is diagonal. You see now map is going much up and down, lots of zigzags. And then to fit in the square, we have to flip that part, which will go down. And these numbers, we just count the number of pieces of monotonicity. So since that map has constant slope, because of this calculation, it will preserve Lebesgue measure. And that's more or less the approach. And with that, what we could prove is that thing. Okay, so if you work in this realm of Lebesgue measure preserving maps, typical map gives you in the inverse limit pseudoarc. So there is really huge set of maps giving you pseudoarc as inverse limit. In the space of interval maps, it's not true. Okay, so this is why one of the reasons that we stick with that maps. I don't have time to show you what was the motivation or how we start to expect that it will happen, but there was some evidence. So before it is known that these maps have these typical maps, Lebesgue measure preserving, they have topological entropy infinite and many other properties. So somehow these maps nicely work with pseudoarc, and we wanted them for some construction that now I want to explain in detail. In fact, in recent years, it was developed very much. So this is technique originally developed by Barge and Martin in the 90s, and it connects inverse limit with attractors. Right, so this is a picture originally from that paper. So what you do, like imagine you have your favorite map on the interval, and what you do, you take arc, and now as it image, you take graph of the map, but rotated. Okay, so this is graph of my map, but it's rotated 90 degrees. And then look what will happen if I do that, and if I now collapse that to the interval, what I will get at the end will be my original map, right? Because I took that interval, I rotated the graph, and I collapse. So this is exactly what I get at the end formula for my original map. Okay, but before I do that, so this is curved, its image is curved, so I have homeomorphism. I can put like identity on the boundary, I can extend it, I will have homeomorphism of the disk. And then in the process of squeezing, in each step I have homeomorphism except the last step when it's no more invertible. So this is this so-called almost homeomorphism, as I told you, a uniform limit of homeomorphism. And then we have this theorem of Brown that Phil mentioned, that if I take inverse limit of these guys, then what I will get at the end will be original space. So in that case, it will be disk. And inside, this is my original map. So this will be this continuum, which will be produced for free. And because of squeezing, if I do it properly, all points for that map will move inside and then finally land here. So this will be attractor. And that's what's in that paper. So that's technique of squeezing plus this heavy machinery of Brown's theorem. So that's like black box for constructing attractors. All right, so this is what I just said. And then some more additional motivation, that is for us, came from papers of these three gentlemen, one sitting here. Yeah, so they made it more advanced because, okay, for Barge and Martin, I had one map. And now the trick is to make it more complicated. Now I have family of maps. Like you can imagine, I have instant maps, for example, that I was showing you before. And then, of course, for each of maps, I can apply separately this technique, but then it's not satisfactory because maybe for each fiber, I will have different maps. So the hard part is to make this continuous transformation. So like apply Brown, because I told you, right, that I make this graph and then I squeeze and then I apply Brown, which is kind of black box. So to get this result, you have to understand very well what's the idea of proof of Brown and make this construction to be in some sense continuous, to not so right, because what's there just to have flavor. Okay, so here I have these spaces, parameterized spaces of inverse limit, but of course I'm using different maps, so these are different sequences. And then Brown for each sequence, space of sequences, tell me how to like take it and plug into this. And because this space changes, then the map which changes this sequence space into the disk is different. So I have to be very careful. And that's what we learned from that, in fact, series of papers. They were very nice techniques, and it was like motivation for us how to do that. So the idea is like simple, but like technicalities are hard, and just for that proof, you have to really understand how Brown's theorem looks like, just to make it make this funny. And there are many different results in there, so I encourage you to look. Okay, and inspired by that papers, we start to look into that space of typical maps, Lebesgue measure preserving. So here, setting this is slightly different because we don't have like family parameterized, but maybe interval, but we have like huge set in the space of all maps. And then like learning from Phil and his colleagues, we just try to repeat it, and that is like short version of what we proved, and it's really similar for what was in Phil's paper, but in for different family and different settings. So here we are in non-compact space of parameters. But anyway, so what was the like final goal, or what was the idea of this type of techniques? What you want to have? So you have like nice family of maps, which gives you interesting attractors, and then you want to have them into the disk in such a way that, first of all, on that attractor, you have your desired dynamics, so your shift homeomorphism. To make it reasonable, you would like to probably that these attractors, when you change parameter, they change in continuous way in Hausdorff metric. So like these parameters mean something. That about weak mixing that we had for free, more or less, because of these typical properties. But what you also want, and what you can do, and what is in Phil's paper, is that in the disk also this attractor is in some sense meaningful, so that large set is attracted. It's not Lebesgue measure, but it's measure coming from Lebesgue measure of that map in some sense. I think I have it here. Yes. Okay, so this is what you get. So you have a Lebesgue measure for your F, then you induce it on this inverse limit, and then the set Bayesian of attraction has a positive measure if you project it. And you recover your measure that you have on the attractor. Okay, so this is type, just to give you, okay, let me go back. So that's what you are fighting for. So have attractor you like, with dynamics you like, with some special measure that you can, in some sense, discover using large set in the disk, and parameter set is reasonable, so attractors and measures change in continuous way. All right. But the problem for us is that, okay, so we use this typical family of maps, which all of them give us pseudo-arc as inverse limits. So all that attractors that we have for this huge family are pseudo-arcs. And we know that two pseudo-arcs are homeomorphic. So there was a risk that maybe you have huge family, you plug it here and you get the same object. Right? It could possibly happen. So I want to go to details. So what at that time we were able to show that we could find some parameterized family, this time by 0, 1, in such a way that for sure we know that there are uncountably many different dynamical systems produced that way. Let's take it that way. Now we can prove that in fact in this family there always are uncountably many non-conjugated maps, but at that time we didn't know that. So we were using prime end rotations number to prove it. So it was hard work, but I'm showing this because that's a question that I think is interesting.
You think non-equivalent, not topologically conjugate? Does that mean?
I will show you. Okay. Yes. So, so I'm on the. That's important that I'm living in the disk. And they are non-equivalently embedded in this dynamic sense. If I cannot find, if for that maps, I cannot send one to the other in such a way that I will send one attractor to the other and I will intervene dynamics. But it's still the map on the disk, on the whole disk. So it's not, I'm not looking only on pseudo-arc itself, but I taking map from disk to the disk, but which sends one pseudo-arc to the other, but about semi-conjugacy, I care only on the pseudo-arc. So it's a little more relaxed than conjugacy, because I don't care what's about dynamics outside. I only want to know that my map is between disks and preserve these attractors. But still dynamics is involved. So I want, on the attractor, I want to commute with the system. So it is less than just non-equivalent embeddings, because then I don't care what's the dynamics of attractors.
This is a little bit bigger than topological quantum.
Yeah, it's
I think this
yeah, weaker. So more general.
more general, yes.
Yes. But still telling you still non-equivalent embedding is more, because it says simply there is no homeomorphism sending one set to the other. What we can show, there is no homeomorphism sending one to the other and intervening the dynamics. And that without dynamics, we don't know how to show actually. It strongly relies on what's going on there. And also that it's from this to this, at least for that paper, it was important that not only dynamics of the attractor, but also that it lives in the disk. Right. I will stop here. Thank you.
Thank you. Do you have questions?
So for your inverse limit attractors, your measure lives on the attractor or on the whole disk? The support of the measure.
Depending which one. So that one, so we have map induced by Lebesgue measure on the attractor. And that is this inverse limit physical for us. Okay, so I have some invariant measure. Exactly to answer. Okay, so I have this attractor, on it I have some measure, and there is, for all maps, there is large set that is attracted in sense of generic points for that measure.
What's the measure outside the attractor?
No, zero. Physical zero. Everything.
Right, so the measure support on the attractor.
No, so that one I'm drawing, it's not invariant measure. It's simply,
No, I know, but you said that basin is a positive measure set.
yeah, for map induced by Lebesgue on,
You just stick the bang on the disk and don't worry about its invariance.
yes. And invariant I have on
You have the invariant on the attractor, but in the disk, it's just the bang, which is not.
yes.
Except the fact that positive measure sets.
So it's not exactly Lebesgue, it's that one induced from this inverse limit of disk. So maybe that's not Lebesgue. But I have Lebesgue on disk, I take inverse limit. And then Brown sends it to that one.
Right, you get a measure, but it's not an invariant measure.
Yes.
Yeah, okay.
Yeah,
that's the other
state release inside of
Yeah, but it's just, right, I mean, you have a non-invariant. measure.
the bag, but on
Also, like for that set, we know that like global attractor, I mean, the full measure is attracted, but for generic, we don't know how to prove it or even if it's possible. So there are many that are, this is unique one, but maybe for some others, we don't know this residual set of maps.
more questions. No, so let's from online over the. For this here. Okay, so thank you very much.